Okay, we're going to do some sample size and confidence level and interval width questions. These are multiple choice questions on beginning on page 188. They do have a weird numbering, as you'll see in just a moment, but we'll begin with problem number one. For a given large sample size, which of the following gives the smallest margin of error in calculating a confidence interval for a population proportion? So first off, let's write down our formula. Just take a look at it. P hat plus or minus Z star, and then we have P hat, Q hat, N. All right. Well, the part after the plus or minus, this part right here, makes up our margin of error. Here's our margin of error. So anything that's being divided makes things smaller. So as N goes up, our margin of error goes down. Anything multiplied makes things get wider. So Z star, as Z star goes up, which is the same as our confidence level. So Z star is our confidence level. So as that goes up, our margin of error goes up. And also as P hat times Q hat, as that goes up, our margin of error goes up. All right, so as P hat Q hat goes up, our margin of error goes up. Those two things multiply together. Another way to say that as P hat and Q hat as they get closer to 0.5, so as P hat gets closer to 0.5, as P hat gets closer to 0.5, our margin of error goes up. So P hat closer to 0.5, our margin of error also rises. So when I do this, confidence level, they say they want the smallest margin of error. Well, that means I'm going to need to go the opposite way because confidence level goes up, my margin of error goes up. So if I want to go down, I want a small confidence level. Well, that gets rid of 95 and 99 and 95. So we know it's going to be 90%. Okay. Now, as P gets closer to 0.5, our margin of error goes up. So 0.23 is closer to 0.5 than 0.15. So this is going to give me the larger margin of error. So in this case, 0.15 will give me my smaller margin of error. Two 95% confidence intervals, two 95% confidence interval estimates are obtained. So basically, if they're both 95%, we know that our Z star is 1.96, so it's not a factor. All right. Now, when I look at this one has a width of 6 because 84.5. So this has a width of 6. And this one has a width of 7.9. So this one's wider. This one has a larger margin of error. So this one has a large margin of error. This has a smaller margin of error. Okay. So if the two sample sizes are the same, so they're saying if the denominator is the same, what has a larger standard deviation? So in other words, which one has a larger P hat or Q hat? The reason I'm saying that is our formula is P hat plus or minus Z star, P hat, Q hat, and N. Well, they told us they were 95%, so that's not going to affect our margin error. They're now saying this, the N is the same, so that's not going to, because they said the sample sizes are the same, so that's not going to have an impact. So which one's going to have the larger numerator? In the larger numerator, as P gets closer to as we get closer to 0.5, or P hat Q hat increases, the margin of error increases. So the second one is going to have the larger margin of error. So that gets rid of this one and this one. Now, I could have also looked at this from the standpoint of, instead of working with this, I could have worked with a T star, X bar plus or minus T star, S divided by the square root of N. Well, they told me 95%, so this doesn't have an impact. They told me my sample size isn't going to have an impact because they're both equal. So which one's going to have the larger standard deviation. Well, that's the one that's most spread out. And why? Because it's in the numerator. So as the standard deviation goes up, the margin of error goes up. So that takes care of the first part. So I'm going to rewrite those formulas, and I have p hat plus or minus z star, p hat, q hat, n. All right. P hat, q hat, n. And here they say if the sample standard deviations are the same, which has the larger sample size? And also I'm going to write it for the x bar plus or minus t star s divided by the square root of n. So in this case, they said the sample standard deviations are the same. Well, we already know that they're 95%, so they're going to have that's going to be the same. We're not going to have to worry about that. Well, they're telling us now that the numerators are the same. And since we're dividing here, as n goes up, margin of error goes down. As n goes up, the margin of error goes down. So they're asking for which one is going to have the narrowest. Well, this one is narrower. So obviously that's our answer, which of course it was highlighted. But because as the sample size goes up, the margin of error gets smaller. So we should have a narrower interval. So this one is going to be C. All right. Which of the following result in a widest confidence level? Well, I always like to start off with the Z star part. So Z star, which means as our confidence level goes up, our margin of error or our interval width goes up. So I'm going to want to choose the one with the largest confidence level. So that means that gets rid of C and that gets rid of A. But then we're talking about sample size. So let's pay attention. As N goes up, our margin of error goes down. But they want the widest, so let's swap this. As N goes down, our margin of error or our interval width increases. So I'm going to want the smallest N will give me the largest interval. So small sample size, largest confidence level gives me the largest interval. In a New York Times poll measuring a candidate's popularity, the newspaper claimed that 19 of 20 cases it's polled should be no more than 3% off in either direction. What confidence level are pollsters working with, and what sample size should they obtain? Well, basically they're saying, you know what? If I did this over and over again, 19 out of 20, which is 95%. So in repeated sampling, 95% of the cases are going to capture it. Well, that means we're working with either D or E. All right, well, they want a margin of error of no more than 0.03. So let's go ahead and write our confidence level formula, our confidence interval formula. So P hat plus or minus Z star, P hat, Q hat, and N. All right, so I know that I can calculate Z star, and I know that my margin of error, or this part of it, equals 0.03. So let's go ahead and calculate Z star real quickly. Second vars, inverse norm, 1 minus 0.95 divided by 2, mean is 0, standard deviation of 1. And we end up getting 1.96 for our Z star. So 1.96. We know we're looking for N, and this needs to equal 0.03. That's our margin of error. When I read this, they don't tell me a P hat or Q hat. And when they don't give that to me, I always have to use 0.5 because that'll give me my widest interval, which is my worst case scenario. So I'm going to divide both sides by 1.96. And I end up getting, and then I'm going to go ahead, and at the same time I do that, I'm going to square this whole thing. So this is going to take off that, and so I end up with 0.25 over n equals an ugly number, 0.03 divided by 1.96 squared. That gives me some number about 0.0078. Now I'm going to keep all of those values. I'm just going to write it down, abbreviate it there. So basically I'm multiplying the two numbers on the diagonal and dividing by the third number. So 0.25 times 1 divided by this number right there. And I get 32, something went wrong. Not sure what it is. So 0.03 divided by 1.96, enter, square that value. Oh, that's what went wrong. This number is wrong. This should be a lot smaller. This should have been 0.00023. And it keeps going on, but I'm just going to abbreviate it there. And so we have 0.25 times 1 divided by this value. And I get 1067.1. We always round up and we get 1068. And in our previous video on sample size calculations, that's where we actually did this problem. So if you want to see this problem right here, this is also on page 187. So page 187, we did the same thing. Okay. A t-statistic was used to conduct a test of the null hypothesis mu equals 0 against the alternative mu does not equal 0. P-value is 0.056. A two-sided confidence interval for the mean is to be constructed of the following, which is the largest level of confidence for which the interval will not contain 0. So basically, what we have is we calculated a p-value and 0.056. Well, this was a two-tailed test, and so they gave us the two-tailed probability. So this area right here is 0.056 divided by 2, and 0.056 divided by 2 ends up being 0.028, and this area right here is 0.028. So at this point, I end up with this amount of space right here, 1 minus 0.056, which is 0.944. Now, here's the deal. Apparently, 0 is somewhere here. I don't know if it's on this side or this side, but I'll just make it here on the upper side. Well, if I go wider, if I make this a 95% interval, all of a sudden 0's not in my rejection zone. Right now 0's in my rejection zone, but if I made my interval go wider than 94%, then 0's not it. Then 0 would not be in my rejection zone. 0 would be in a white spot. Because remember, the tails are the rejection zones. All right. So that means my 95, 98, and 99 are gone. And it said, which is the largest interval for which will not contain 0? Really 94%, they didn't give 94%, so we'll have to use 93%. And it wouldn't have mattered if I'd put the 0 down here. Once again, if I widen this, it widens equally in both directions. So that would also, if I'd gone this way with it, it still would have contained it if I go to 95 or 96 or 97, et cetera. So increasing my confidence level widens this interval. Because the confidence level goes up, the margin of error or width goes up. So if I increase it, it gets wider. In this case, we're right here because that's our p-value. So I need to not go wider. I can go as wide as 94.4, or I can make it narrower. If I make it narrower, then you can see that it would still be in the rejection zone. So the largest one not in there is 93%. Sure, 90% also wouldn't contain 0, but they say what is the largest level that does not contain 0, and in that case it's 93%. Okay, so the school superintendent wants to know what percentage of property owners are willing to support an increase in school taxes. What sample size should be obtained to determine with 90% confidence the support level to within 5%? So they want a margin of error equal to 0.05. That's the 5%. 90%, so we're gonna have to do a Z star based on the 90%. So let's do that real quickly. Second var's inverse norm, parenthesis 1 minus 0.90, close parenthesis, divided by 2. And I end up getting 1.645. So that's my Z star. My formula for confidence interval, P hat plus or minus Z star, P hat, Q hat, N. This part right here, after the Z star, is my margin of error. So 1.645 N, and then equals 0.05. Now, when I look at this, the one thing I noticed, they did not give me a P hat. When they don't give me a P hat, I'm going to have to use 0.5. At this point, I'm going to divide both sides by 1.645. And that's gone away. And now I'm going to square this whole thing. So this gives me 0.25 over N equals 0.05 divided by 1.645. And I'm going to go ahead and square that. So I get 0.00092, etc. And I'm going to take 0.25 right here divided by that super small number. And I get 270.6. We're always rounding up. Best answer is 271. A political action group wishes to learn the governmental approval rating on the environment, or wishes to. So from a past study, they know that they will have to poll 270 people for the desired level of confidence. So this is what they originally polled. If they want to keep the same confidence level and have a margin of error of 1/3 the size, how many people will they have to poll? This is my own formula that I've kind of created. It seems like it's something to students, so you might want to try this. 1 over, now granted, I hate giving you formulas to memorize, but this seems like it helps a lot of people. 1 over the square root of new over original equals the ratio. So in this case, this is going to be 1/3, because they said they want it 1/3 the size. So 1 over, now I'm just going to put N for new, over what the original was. Well, the original size was 270. And they want this to equal 1/3. Well, I'm going to go ahead and square everything. So this becomes 1 over 9. This becomes 1 over N divided by 270. I'm going to make this a double bar fraction line. And I'm kind of run out of room, so I'm going to go on to a little scrap sheet of paper. So I have the double bar fraction line. So 1 over the double bar, N divided by 270 equals 1/9. So I'm going to flip this, and I'm going to go, well, 270 over N equals 1/9. So that simplified that fraction up a little bit. And I can multiply the diagonal. So 2 and divide by the third number. So I'm multiplying these two, dividing by 1. So if I go 270 times 9, I end up getting 2,430. And that, in fact, is my answer. All right. So basically 1 over new over the original. All right. The square root of that. And here's the way you use it. So in a random sample, number 7, in a random sample of 450 adults, 28% said that they felt that their credit card debt is too high. With what degree of confidence can the pollster say that 28 plus or minus 4% of adults believe that their credit card is too high? So first off, this is my margin of error. All right, that's my margin of error. Let's go ahead and write out our formula. So our confidence interval formula is p hat plus or minus z star p hat q hat over n. Well, this part right here needs to equal 4%. So 0.04 plus or minus, well, actually, I'm sorry, 0.04 equals, because this is the margin of error. We don't know what z star is. That's what we're going to have to calculate. We know p hat is 28%, so this is 0.28. This is going to be 1 minus 0.28 or 0.72. And we know we had 450. So let's simplify this part right here. So 0.28 times 0.72 divided by 450. And we'll go ahead and take a square root of that. So I'm going to raise it to the half power. That takes the square root of it. So I get this value here. So I end up with 0.04 equals z star times 0.021166, and it continues on. All right. So I'm going to take that 0.04 and divide it by that value. And I get 1.8898. Well, that's not a probability. That's my z star. Okay. So basically, here's what's happening. If we were drawing a normal curve, a normal curve, I end up with 1.88898 is my upper, and my lower is going to be negative 1.8898. All right. And so now I need to calculate my confidence interval. So how much area do I have in between there? Well, I can do a norm CDF. And remember, these are z-scores. And since they're z-scores, I have a mean equal to 0 and a standard deviation equal to 1. So second vars, norm CDF, lower bound, negative 1.8898, upper bound, 1.8898, mean is 0, standard deviation 1, and I get 94.1. There it is. Okay. Tricky problem. A guidance counselor wishes to determine the mean number of changes in academic major by college students to plus or minus 0.1 at 90% confidence. What sample size should be chosen if it's known that the standard deviation is 0.45? So here we'll be careful. Here we're looking with mean. All right. And I'm going to pause this for just a moment, get a drink of water. Okay, excuse me. So anyway, we're talking about a mean here. So since we're talking about a mean, we need to be working with x bar plus or minus z star standard deviation divided by square root of n. Even if it were a t distribution, work at it this way because we have there are degrees of freedom issues. So if this had been a t distribution, still work with a z here, and things will go much better. So they want it to be plus or minus. So this part right here is our margin of error, and they're telling us it needs to equal 0.1. So let's go ahead and calculate our z star. By the way, we know this standard deviation, they tell us is 0.45. N is what we don't know, but we can calculate z star real quickly. So second bars, inverse norm, parenthesis, 1 minus 0.90, close parenthesis, divided by 2. Mean is 0, standard deviation of 1. Calculate. So we end up getting z star equals 1.645. So 1.645 times 0.45 over the square root of n needs to equal 0.1. So I'm going to go ahead and do some math here, multiply those two values. Clear 1.645 times the 0.45. That gives me 0.74025 over the square root of n equals 0.1. I'm going to go ahead and square this whole thing. And that's going to give me, and I'm going the wrong direction, but I just didn't allow myself enough room. So 0.74025 squared is that value. I'm just going to write down part of it, 0.54797 over n equals, and we also had to square the 0.1. This is going to be, when I do that, it should give me 0.01 equals 0.01. Put that over 1. I see I have a proportion. So these two are getting multiplied, dividing by a third. So let's get that value back. Want that value divided by this. And 54.7, we always round up. So that takes us to 55. Okay, that's number 8. And we have problems 9, 10, and 11. So two confidence intervals estimates from the same sample are 77.2 to 72.2 to 77.8. So let's find out how wide that is. 77.8 minus 72.2 is 5.6. And this is 78.7 minus 71.3. And this is 7.4. All right. So they're from the same sample. One estimate is at the 95 and the other is at the 99%. Which is which? Okay, so as the confidence level goes up, the margin of error or the width goes up. So since this is narrower, this is going to be the 95%, and this is going to be the 99%. All right, this will be the 95%, this will be the 99%, so our answer is A. In general, how does doubling the sample size change the confidence interval size? Well, I'm going to go back to that formula I gave earlier, 1 over the square root of new over the original. And this time, our effect is we don't want 1/3, we want it to be 2 times as wide. Well, they didn't give me an original size and they didn't give me a new size. So let's go ahead and figure this out. Let's start off with an original size. Let's just say we had an original size of 100. Okay, so if we had an original size of 100, we doubled it, we're going to have a new size of 200. So we're going to have 1 over The original size, we just chose a number, 100. We're going to go ahead and double that and make it 200 and see what happens. So when I do that, 100 goes into 200, that goes twice, equals 1 over the square root of 2. Well, what's that mean? What's the square root of 2? 1.414. So what we end up doing is dividing by, dividing by 1.414, and that's supposed to be 200. All right. And it wouldn't have mattered what two numbers I've chosen. I could have chose, as long as this one, the numerator was twice as big. Let's say I chose 1 over the square root of 600, so that my original had to be 300 because that's twice as big. So 600 divided by 300 is 2. So once again, square root of 2. Lastly, number 11, a 90% confidence interval is to be created to estimate the proportion of television viewers in a certain area who favor moving the broadcast of late weekend news to an hour earlier than it is currently. Initially, the confidence interval will be created using the sample size 9,000. That's a big sample size. Assuming that the sample proportion does not change, what would be the relationship between the width of the original and that created on a sample of only 1,000? So once again, we're going to go to that formula, which is 1 over the square root of new over original. Well, in this case, our original was going to be 9,000, and our new is 1,000. Well, my zeros cancel out, and actually I can just go 1,000 divided by 9,000 is 0.11. Actually, let's just leave it as 1/9. Let's leave it 1 over 9. We can do that, which equals 1 over the square root of 1 over the square root of 9. So this would be equal to 1 over 1 divided by 3. Now remember, they flip over the double bar. So 3. So 3 times as wide. And remember, as n goes up, the margin of error goes down. As n goes down, the margin of error goes up. Well, our n in this case went from 9,000 to 1,000, so our n went down. So we'd expect our margin of error to go up. So how much did it go up? It went up by 3 times because of the square root of that square root function that's in the denominator. All right, thank you.